Hello guys, I'm Sandip. So today we are going to continue our session in which we have started in the previous lecture, right? So in the previous lecture of this session, we have studied about the different forces. If you do remember, there is the weight of the object, then normal reaction, tension, and friction. So basically, we can say we have studied a lot of things about the force chapter, right? So in that force chapter, these are the different types of forces. We know the four fundamental forces, right? Yes, can we recall the fundamental forces? First one is gravitational. Second, electromagnetic force. Third one is strong nuclear force. And fourth one is weak nuclear force, right? So these are the different types of forces we know. These are the fundamental forces we call it. And I specially asked you to remember one of the forces that is the weakest force. Which one is the weakest? That is our gravitational force, right? Then we also studied about all these different force, that is weight, normal reaction, tension, friction, right? All these forces also. Okay. So most of the forces we have studied, those were on the solids, right? And we haven't talked about much about the liquid or the forces on the liquid. Right? So today we are going to study the new concept, right? Which we can say, which is a step ahead of the force, right? Force quantity, right? And that concept is a pressure, right? So pressure, we can say pressure acts on the solids also, or liquids or gases. So pressure could be everywhere, right? Even the force also we can say it could be everywhere. Or we can study the force in liquid also, or air resistance is also a force in the air, right? So, but pressure we can talk about solids as well as liquids. So we are going to talk a little bit about the liquids in this pressure concept. Okay. So now tell me, where you have heard this term pressure in our home? Pressure cooker. Can I say pressure cooker? Yeah, that's right. Okay. So we know about the pressure cooker. So what is the work of that pressure cooker? Right? Yeah. So we know one thing that normally we use the pressure cooker for boiling or cooking the rice, most probably, right? Okay. So why we are using the pressure cooker instead of our normal pan, we can say, right? Because pressure cooker is making cooking easier, we can say, right? Let's not go into detail of that, but can I just say that it will take a less time if you use the pressure cooker instead of our normal pans. That's why we use the pressure cookers, right? Especially to cook the to boil the rice, we can say, right? So simple thing we can say, it is easier, it is time saving when you use the pressure cooker. So obviously the word there is a pressure, can I say in the pressure cooker there will be some pressure? We don't know it what is pressure, right? But let's say there is some pressure, right? Okay. So if this pressure quantity is present in pressure cooker, boiling is easy. Very simple to understand. That's right. Okay. Now let me tell you one more thing. Right. We live on the earth, right? But earth is not completely flat, right? What we can say, earth has the mountains, right? Which are at very height, we can say, right? They have a very large height also. And the sea level is also there, right? And middle part is also there. So earth is not completely flat, it is something like this, right? Sometimes mountains are very high, right? So this pressure thing is more at the sea level. Remember what I'm saying, pressure thing is more at the sea level, right? Which is near to the sea, obviously, right? And when we go on to the mountains, right, on mountains, pressure will be very high, sorry, pressure will be very low, right? At sea levels it will be high, and at the mountains at the top we can say pressure will be very low. So tell me one thing, where should it be easier to cook the food? Right now you can take the reference of our pressure cooker, right, and think on that, where the cooking food should be easier. Will it be at the top of the mountain or sea level, right? Obviously, we know because of pressure cookers makes it easier. So if the more pressure is there, boiling or cooking food is easier. Where is the more pressure at the sea level, right? So if you do one thing, consider you are at the sea level, your friend is at the top level, we can say on the mountain, right? If you use the same, let's say, boiling unit, right, heater or gas, or you just used our normal fire, right, or burning fire, burning wood, we can say, and on that you want to cook the food. Again, it is very simple to understand that pressure at the sea level is very high. Therefore, you will be able to cook your food earlier than your friend who is sitting at the top of the mountain. Okay. Okay. So now let's see what we are going to study in this chapter. So as I said, first of all, we will study about the pressure. Pressure could be between the in the solids or liquid or gases, right? Then pressure inside the liquid, what is the significance of that? What are the formulas for that? We are going to study those two. And the third one is the atmospheric pressure. Now we already know, right? We are surrounded by, Earth is surrounded by atmosphere, and that atmosphere is very essential for our life, right? If there is no atmosphere, if you can consider on moon, right? On moon there is no atmosphere, so there will be no life, right? It's not easy to live on the moon, right? Even now the human beings are trying to uh, move on the Mars also, right? They want to colonize there on the Mars. Also, it is not very easy. There are a lot of conditions, a lot of situations we have to go through. Then only we can go to the Mars, right? Now it is not today's occurrence, we can say, right? It is going to take a lot of years, and most probably when you grow up to some particular age, you may become the uh, person to go on to the Mars, right? If you are interested in that astronaut thinking, astronomy, etc. Okay, so as we were saying, atmospheric pressure, right? Earth has atmosphere, so if there is an atmosphere means what? It is nothing but the mixture of gases, right? Which gases are most in our Earth atmosphere? Nitrogen is there, oxygen is there, right? Nitrogen, oxygen are the most found gases we can see in our atmosphere. Then we have the carbon dioxide and other gases in small amount, obviously, right? Okay, so let's start. Now, what is pressure? We already have talked about the force, right? Now, if we know the force, we can calculate the pressure. How? Very simple formula, that is force upon area, right? So here, we can see one small image there, one diagram there. These are two knives, right? You can see this is very sharp knife, so the first knife is very sharp, right? It has a point there exactly, and this other knife has a very large area, right? After using a lot of time or long time, knife do becomes like this, right? So what you can see, the point has a very small area, we can say, right? And this knife, which is broader, has a large area. So which one do you think will be easier to use, easier to cut any fruit, we can say, or vegetables, right? Obviously we need the sharp knives. If it becomes after a long time, we do bought the new knife, we can say, right? Why? Because of this pressure, right? Because force, what is pressure's formula? Force upon area. Force, I know how we can use the force. We are applying the force, that is muscular force, we can see, right? So for the same force, we apply the same force. The sharp knife, as it has the small area, and area is in the denominator of the formula of pressure, so it is going to apply more force compared to your other knife, which is, we can call it as a dull knife, right? Which is being we have used it for a long time, we can say, and this is our new knife, not life. Okay, so pressure due to this sharp knife will be more because it has small area, and as the area is small, I can say pressure is inversely proportional. Inversely proportional meaning what? P is equal to force upon area. Area is in the denominator, so I can say P is inversely proportional to area. Simple meaning, if the area is less, force will be, or pressure will be more. Pressure will be more. So which area we are talking about? The definition is the force acting upon a unit area. It's called as pressure. So on whatever area the force is acting, we have to consider that much of area. Here for the second nail, we have to consider this whole area, right? Obviously it is greater than our smaller area. So for the same force, sharp knife is going to apply a lot of pressure there. Okay. So here you can see the formula: pressure is equal to force upon area, or I can say area is equal to force upon pressure, or force is equal to area upon pressure. Very easy to understand, right? Not at all difficult. Now, let's take one example on this case, right? Consider we want to hammer one nail into the wall. Right? Tell me, you will use like this or like this? You will hammer from this side, from this side, right? Obviously we will hammer on the head of the nail, we can say. Why? Because here the area is more area. At the point similar to our knife, what I can say, area is less. So for the same force, that pressure of that nail part, we can say, right, pointy part, it is going to be more. If it is more, it is obviously going to go inside the ball. You can try this one, but I don't think it will ever go into the wall, right? This part, this is head part, flat part, we can say, of the nail. Okay, very simple to understand. Now consider one more thing. Suppose you must have visited the car station, right? Car garage, we can say, with your dad, right? So suppose in that car station there is lift, we can say, right? And they want to, lift means not normal lift, but there is a station for the car where they lift the car up, right, in the air, then from the downside, from the downward side, they repair that car, right? So how, have you ever noticed how they actually lift that car? Is anybody, there is one platform right there, and on that platform they keep the car, and then they raise that platform using what, right? Obviously using pressure, you can say, right? So again, whatever is the pressure, we need the, in this case area will be bigger, we can say, because car needs to be on that, right? Okay, so here we actually use one principle, right, mentioned by one scientist, which is, who is Pascal's scientist, Pascal scientist. So what is happening in this case, right? This is called as actually hydraulic lift. Hydraulic is something like, we can say, or we have to apply some force on that piston. So this area is small and this area is large, right? So here we are going to apply some small force. Obviously to lift the car we will need the bigger force here. Let's call this as F1, let's call this as A1, right? So this area, let's call this as area as A2, and force which is going to push that platform, let's call this as F2, right? So this Pascal scientist was there and he said, right, let me write the name here, Pascal's. Okay, he said pressure developed at the, let's say this first point is equal to pressure developed at the second point. So can I say Pi is equal to, let's say, P2. Therefore, he used the formula F1 upon A1 is equal to F2 upon A2. Right? So F1 upon A1 means if you apply some force on here, smaller force on smaller area, as the area is larger in this case, it is going to raise that platform with a higher area, we can say. Let's try to solve one small numerical on this. I will draw the diagram here again. Say this is Pascal's law. This is actually called as Pascal's law. Right, I will draw one diagram again here. So this is our car and this is the platform we want to move up, right? Okay, so this is our car. So what we are doing, we are applying some force F1 here on the area A1. This is our F2 force, which is lifting this area A2. Okay. So as I said earlier that P1 is equal to P2 we are supposed to consider. Therefore, can I say F1 upon A1 is equal to F2 upon A2. So assume this area, this small area, let's say 10 unit. What is if we want to lift the car's mass, let's take car's mass is, let's say 600 kg, right? And what force should we apply on that to lift that car? Obviously force should be equal to mg. We have studied this one, right, in the first session, that if the mass is 600 kg, the weight we need to calculate, right? So weight is equal to, let's say 600 into 10. Why 10? G approximately we can take it as 10. So let's say 6,000 newtons we need. Okay. Consider this area A2 is 1000 unit. Okay. So area is very small. Now we need the force 6,000 here. So doing this calculation, what I can say, I have to apply, let's say force of only 60 Newton. If I apply the force of 60 Newton, if you calculate this F2, you will get 6,000 Newton as answer. So we can easily apply the 60 Newton force, right? We already have seen that weight is, if the mass is 40 kg, weight is almost 400 Newton. So if you only stand on that piston, then only that car will get raised, right? So this is the very important application of the pressure that Pascal law said that pressure at every point in this enclosed cylinder, this is called as enclosed cylinder. So Pascal said the pressure of the liquid or fluid, we can say, in the enclosed cylinder remains same, and that enables us to lift that car using a very small force, right? Okay. So this is the pressures formula and pressures applications, we can say, in our life. Okay. Now, as we were talking, this is about the liquid, right? So you can say this is the pressure in liquid. Let's solve one more example on pressure in solids. Right? We have already seen the example of knife. We have already seen the examples of nail and hammer also, right? Okay. So consider if I am applying some force on, consider this 10 Newton is the force, and this area is, let's say, 5 meters square. Using this, can you try to calculate the pressure? Yeah, formula is very easy, right? Pressure is equal to force upon area. So substitute the values, 10 Newton divided by 5, right? Simple calculation. So you can calculate the pressure to be 2 Newton per meter square, right? So this will be 2 Newton per meter square, or there is another unit for this pressure, which is called as Pascal, right? As we know, Pascal is a scientist here. So we know that the units are named after the scientists, right? So Pascal studied this pressure. So for the pressure, they have given the unit of Pascal. If you study hard and found out some another quantity on yourself, they will give you name of U to the unit of that quantity, right? Remember this. Sure. So next. So let's talk a little bit about the pressure inside the liquid. Okay, so this is a very small plastic can, we can say, right? We can see the lot of cans. Even for drinking water, there is a can and there is one tap, we can say, which we open and we can get the drinking water, right? That type of can is there. Instead of tap, now uh, 4 holes are made here, like this, right? Obviously, if the can is full, what is going to happen? That water is going to flow through this hole. Yes, we can see that too. But can you observe by what speed that water is coming out through the different holes? There are 5 holes actually, right? Just compare the last hole and topmost hole. What you can see in that case, right? Here you can see this is how the flow of water is, and in this second case, this flow is like this, right? Where is the more pressure? You can see obviously, right? The speed is more, distance covered is more by the lower hole, I can say. So the pressure at the lowest point, right, bottom point, I can say, bottom point will be more compared to our topmost point. So this is the very important condition in the liquid, that pressure pressure increases with the depth, right? Again, I will repeat, this is the important point inside the liquid. Pressure increases with depth. Depth means what? From where we should measure? This one or this one, right? So sometimes we can call it as depth, or sometimes we can also call it as height also, right? So this is the height or depth, right? Simple thing, right? Now there is one question I'll ask you. You must have heard of the dams, right? So there are many dams in our country. So you may visit the dams, right? You may have visited the dams, obviously, right? So dams is something like this. We cannot see those bottom part, but these are like this. Bottom parts are like this, right? This wall is not completely straight. It is like this. When it is going at the bottom of the dam or lake, we can say dam most probably, this wall is getting broader and broader, right? Why that wall is getting broader? Now, first of all, tell me the purpose of the dam. What dam do? Dam actually stores the water, rainwater, we can say, right? In rainy seasons, there is a lot of water, and we may have seen a lot of floods and etc. and etc. And what happens in summer? In summer, there is lack of water, we can say. So what human did, they built a lot of big dams, right? So those dams can actually store the water from the rainy seasons, and we can use those water in the summer season, right? So these walls are actually stopping the flow of this water, right? Do you think it is very easy to stop the flow of water? No, right? We must have seen the waterfalls or rivers, right? Rivers in the very high velocity water running there, right? So this water also applies some force, we can say, on that wall. So if that wall is not big enough to hold that flow or hold that force, what will happen? That wall will break. So actually, that water is applying the pressure, we can say, on the wall, right? So as I said, this wall is the broader at the bottom, right? Why is it like that? Here we have discussed in this diagram, in the previous diagram, we have seen when we increase the depth, pressure of the water is increasing. So can I say that the water at the bottom hole is going to apply more pressure than that of at the or top, right? Similar thing happen in case of dam also, right? Water at the bottom is going to apply a lot of force here compared to at the top. Therefore, to stop that pressure, to stop that force, we can say this wall at the bottom is very broad compared to top. Okay, so remember this concept about the dam. Okay, now what is the pressure of the water considered in, let's say, liquid? If you want to find out the pressure in the liquid, right? Suppose this is the dam, and we want to calculate the how much is the pressure here at this particular point. Means, suppose consider there is one person swimming right inside the water. Normally we swim at the top only. We don't go inside the water, right? Like this is swimming. Okay. So obviously it is difficult for us to walk or swim than walking, right? Walking is very easy. Swimming is difficult. Why? Because air cannot apply that much of pressure or force, we can say, but water do. Water do apply a lot of force, right? Or pressure. Okay. So when we are actually swimming, this person is swimming, he has to overcome the force acted by the water. So if force, water is acting the force like this, right? The swimmer has to overcome that force, we can say. Okay. So tell me, is it easier to swim at the top? Right? Use this application, which we concept I have told you, or it is easier to, let's say, swim at the bottom. So bottom, we can say, a little bit of down or depth, where it will be easier to swim, right? Obviously, at the top it will be easier. Why? Because pressure on the bottom will be high. So yeah, we can say water is applying the more force there, right? Simple. So in solids, what we have seen, if the area of the application is small, then pressure will be more. In liquid, what we can say, if the depth is more or height downside is more, then we can say pressure will be more, right? Okay. So how much is that pressure actually? Let's talk about that. Now, instead of this swimmer, let's consider I keep one, let's say, any object there. If I kept any object there, then this water is going to apply pressure on this object from all sides, obviously. Even on the swimmer, water applies the pressure on the from the all sides, right? So this pressure's formula is given as, we are not going to derive this right now, but we'll just remember this formula. That is rho g into h. Okay. So formula is what? Formula is rho into g into h. Now let's try why we got this formula. Consider we know the normal formula for the pressure is force upon area. Forces means what? Can I say it is mg? That is weight is our force, right? So if object is there, there must be some weight. Area. Now for this mass, there is another concept which is called as density. So density is, remember, density is equal to mass upon volume, right? So I can say mass is equal to, it becomes rho into v. Density is also very important concept in terms of fluids or liquids. We are going to say what is density and how it works. We will see that too, no problem, right? So let's substitute here rho into v into g upon a. And volume, if you consider the volume, consider this is the small cube, you know how to calculate the volume, right? This is L into B into this is B, right? And this is height. So what I can say, volume is equal to L into B into H. Also, I can say L into B is what? Area. So volume is area into H. So what about volume upon area? Volume upon area will give me H. So here you can see volume upon area. So can I say this is rho into H into G? That's right. Okay. So pressure acting on that object due to that water is rho into H into G, where rho is, what is rho? Very important concept. Rho is density. Density of water in this case, right? Because there's the ocean. So obviously oceans are made up of water. So we can consider water. So for different liquids, the density is different, right? If you consider, let's say, oil will have less density than that of water. So it will be easier to swim in the ocean of oil, right? Remember that. But obviously there is no ocean of the oil. So we don't have to worry about that. Okay. But it would have been better. It would have been easier to swim on into that. Okay. So one more thing I want you to remember is this rho of water. the value is equal to 1000 kg per meter cube. Don't worry about the unit right now. Just remember 1000 is the density of water. So if I know the height of the object, or this is the height, let's say consider, let's consider this as 50 meter is the height, right? So I can calculate the pressure at that point. Wait, I don't even need the what is the object, is it swimmer or this block or this wall, doesn't matter. I just need the density of water, I need the height or depth we can say, and the value of G. Value of G approximately how much we take the value of G? 10, right? Let's try to solve this question. So rho GH is the pressure, right? So let's write P is equal to rho GH. Rho is 1000, G is 10, height is 50. So how much will be the pressure in this case? 50000, right? So there are total 5 zeros. Pascal we can say. Okay, so this will be the height at that depth. So you can see it is a very big height, right? So if this wall want to sustain that pressure, obviously it should have a very broader size, we can say. Okay, so this is the pressure inside liquid. Now, so now let's talk about the atmospheric pressure. Now we know about the pressure inside the liquid, right? For that, the important concept I told you is the density. Density of water is how much? 1000, right? Okay. Now atmospheric pressure, right? Atmosphere means I already told you that Earth has atmosphere, right? Moon does not have any atmospheres, therefore we cannot live there, right? Earth has atmosphere. Atmosphere contains a lot of gases there: nitrogen, oxygen, carbon dioxide. Main constituents are nitrogen and oxygen. We know that part. Okay. Now we have seen that water or any liquid is obviously, for any liquid in the depth, if there is sufficient height or depth, we can say, obviously there is some pressure, right? So those water is acting some force on the object. Similarly, this gas is also does this thing. Even air, right? Atmosphere does the same thing, right? How they can do the? Is it possible that air is applying some pressure? Yes, obviously. Why not? Because you can see air has some molecules like this, right? These molecules are randomly, uh, we can say, moving in random directions, right? Different directions. These molecules are going to give you apply some pressure, even though we cannot actually, if you are sitting or standing, obviously we are not going to able to feel that pressure, but there is the pressure due to air also or atmosphere also, right? Now, what is this pressure's formula in the gas? We can say it is K. K is constant. Density of air we can consider. Temperature. Now, obviously, temperature is different at every place, we can say, right? In the world, there are many different places where the temperature may vary. Some places have the very cold temperature, very low temperature, we can say, right? And the desert areas will have the very high temperature. So on that temperature also pressure is dependent. And molecular weight. So molecular weight of the gas, whatever gas is there, if nitrogen is there, oxygen is there, what will be the molecular weight? It is all related to chemistry again, right? So we can find out the molecular weight of the gas. And using this formula, we can find out the pressure, right? Now we understood one concept that if there are a lot of air molecules, then there will be pressure. Now, low pressure and high pressure. I also told you at the start, if you do remember, at the sea level, there will be high pressure, and at the top of the mountain, pressure will be less. Right? Also, remember for the hot gas, these molecules are moving, but moving with the more speed. So remember, this will have more speed than the cold gas. More speed. So if the speed is more, obviously pressure is also more. So can I say that pressure of the gas depends on the speed also? Yes. And speed depends on what? Temperature. If the temperature is high, very simple to understand, right? If in the cold in the winter normally we do not like to go away or move lot, right? We want to just sleep at the late in the morning, right? We do wake up or very late in the morning in the winter season. But in summer, what we do, we need some energy, right? We try to go somewhere, right? Because if the temperature is high, molecules are have more speed, right? We can say. So more speed will give you more pressure, right? So hot gas, we can say, will have more pressure than that of cool gas. Okay, so this is the one thing we can say. Now, obviously, this will have less speed, right? Less speed, less pressure. Okay, so we know that pressure varies from places to places depending on the temperature of that places, and who is going to apply pressure? Those molecules which are moving randomly. Okay, next. Now, atmospheric pressure is what? Okay, so this is the column, right? You can see the earth there, right? And on this earth, for the sea level, we can consider column of air extending from sea level. Sea level means close to the level, we can say, to the upper atmosphere, right? So we know there is atmosphere also has some range, right? So for that range, we have to consider one. Let's consider one imaginary column, right? Imaginary column which has the area of 1 meter square. So this area is 1 meter square. We don't have to manufacture it and keep it like this, right? It is very high. It is very high there, right? It is the imaginary column, we can say. Okay, so this is the column of air for whole atmosphere, right? And this column, obviously, we know the pressure, right? Pressure means there is force and there is area. All those things are there. So obviously, we will need some area. Therefore, we are considering this column, right, of the atmosphere. So area will be 1 meter square. So this column is going to create some pressure. We know that water creates some pressure, right? At the height, at the depth, we can say. Similar, this column is going to create some pressure at the sea level or on the earth, we can say. And whatever pressure it is creating, that pressure is called as 1 atm pressure. So this is called as 1 atm pressure, means 1 atmospheric pressure. So this 1 atm is also the another unit of pressure. Okay, we already know one unit. What is the unit? If you do remember, it is named after one scientist, right? That is Pascal, we can say. So 1 atmosphere is also unit. 1 Pascal is also unit, right? We know that many quantities have different units. Even our length, we say we can measure the length in meter also, in centimeter also. You might know that 1 meter is equal to how much? 100 centimeter, right? Similarly, there is also conversion between these two, right? So I can say 1 atm is equal to 10 raised to 5 Pascal. 10 raised to 5 Pascal means there are 5 zeros on 1, we can say, right? So 1 atm is 10 raised to 5 Pascal. Simple. Okay. So this is the pressure of the atmosphere. Remember, at the sea level. Right. So when we talked about cooking food at the sea level, we have the 1 atmospheric pressure, and at the mountain at the top, obviously that pressure will be less, right? Okay. So this is what we can say about the atmospheric pressure. Here you can see now, as we said that at the sea level pressure will be high, and at the top of mountain pressure will be low. Why it is like that? Right. Here you can see two there, right? One will be at sea level and one is at the top, right? What is the person who is at the sea level saying? He's saying, look at all the atoms pressing down on the guy at the bottom of the mountain. So here you can see the column, that air column, right? Here there are a lot of molecules. Many molecules are there. At the top you can see there are very few molecules. So look at how few atoms are pressing down on the guy at the top of mountain. So atoms or molecules, we can say. So here are very less molecules. Therefore, they cannot apply a lot of force on the person here. But on the person who is at the sea level, pressure will be very high because all the molecules are applying some pressure, right? Okay. So therefore, we can say at the sea level pressure will be high. And what is the pressure there? That will be 1 atmospheric pressure. Okay. Obviously, here it will be less than 1 atmospheric pressure. Okay. And as we talked about this, that cooking will be easier at where? Sea level or the top? Sea level, right? Cooking will be easier because pressure will be high, and we can consider our example of pressure cooker. In pressure cooker, pressure will be high, so cooking will be easier, right? Similar. Then, now this is the instrument. This is one instrument which is called as mercury barometer. Mercury barometer. Now this mercury barometer is actually used for measuring the atmospheric pressure. Now we said that here is 1 atmospheric pressure is there. How to decide it is 1 atmospheric pressure, right? We can take this instrument right here at the sea level and place it here. So consider at this point I place this instrument, right? How it is going to measure it is 1 atmospheric pressure. Let's see. So mercury barometer, right? So can I say it is filled with the mercury, right? So what is going to happen? This is one small tube is kept here, right? Mostly 100 centimeter or 1 meter tube is kept there, and obviously we know that air is obviously applying some pressure on this mercury or liquid which is kept in this container. So if air is applying some pressure, can we say that liquid can go into the tube also, right? Liquid has the option to go into the tube. So it is going into the tube, you can say. So it depends on how much pressure that air or air column is applying. Obviously, we know that it is going to vary at the different distances or different depth. At sea level, it will be more. At the mountain, if you take this same instrument at the, let's say, mountain, this person has this mercury barometer, right? Pressure or force applied by the air will be low. Why? Because the molecules or atoms are very less there, right? So that they will not be able to apply more force. So liquid going into the tube will be less in the top case, we can say, right? So let's see what happens at the bottom. Pressure of the air column is such that this mercury liquid goes up to this point, and this length becomes, or this height becomes 760 mm. 760 mm, or I can say 76 centimeter, or I can say 0.76 meter, and one word is added to it, that is Hg. Hg means in chemistry's periodic table you have this Hg as mercury, right? So remember this one. So 76 mm of Hg. So what we can say, at the sea level the height we got in the mercury barometer always, right? Always, it is not changing anytime. Right? So we are going to get 76 millimeter of Hg height. So I can also say at sea level, pressure due to air column, we can say, is 760 mm of Hg, or I can say it is 76 centimeter of Hg, or 0.76 meter of Hg, right? So this becomes another unit of our pressure, right? So we already talked about the Pascal. Pascal is our standard unit, right? Which is named after one scientist. Atmospheric pressure, we also know that unit. Now this is the another unit, and at sea level this is the column of the Hg, means Hg moves upward by through this distance, right? Now we have already talked that at sea level this is the pressure, and it is also equal to 1 atm, right? So can I say 1 atmospheric pressure is equal to 760 mm of Hg pressure? That's right. So 1 atmosphere means, either we can say 1 atmosphere is 1.013 into 10 raised to 5 Pascal, or I can also say this like this: 1 atmospheric is 760 millimeter of Hg, right? Okay. So how to measure that? We know the pressure's formula. Pressure formula is what? Rho into GH, right? Let me write this: rho into G into H. This is my formula. What I can do, I can substitute the value of rho is what? Density. Density of water is how much? 1000, right? But now are we using the water here? No. What we are using? We are using the mercury. So we need the density for mercury. I'll write the density for mercury here. Let's say density of mercury is equal to 13600 kg per meter cube. Very high, right? Very high compared to what our water's density is only 1000. So this is 13600, very high. Right? Let's try to substitute here. 13600. G is approximately for calculation we can take, right? And what is the height? Height is 760 mm. But we need the SI unit, right? Standard unit. Standard unit is 0.76. Right? So we have to do this calculation. Right? So 136, this will become, I guess, 136 into 76 into 10. Okay. Let's try to do this calculation by our normal method, right? So 136 into 76, how I can do this? This becomes 6, carries 3, 18 plus 3 will become 21, carries 2, this is 8. Again, give 1 0, 42, 7 6 are 42, right? Carry will be how much? Let me just 2. Okay. Carry will be 4. 7 3s are 21 plus 4 25, and this becomes 9. This 6 3 3, and I can say, okay, where it gone? I have to do this calculation again, I guess. Okay, let's write 136 76. So 36 21 and 8. We again got this sum from somewhere. Okay. So I can say this is 6 3 3 and 10. Just a minute. Let's do it here. How much? 136 into 76, right? Let's do it again. So 3 1 8 0 7 6 are 42, carries 4 25 2 9. This becomes 6 5 13 10, right? So this is almost 10356 into, you can say, 10. Approximately it will, if you use the 9.8, this will give you the value of almost 10130, which is equal to 1.013 into 10 raised to 5. If you do remember, this is nothing but our 1 atmospheric pressure. This is the value. This is Pascal, right? This unit is Pascal, and this is nothing but our 1 atmospheric pressure, right? Okay. So therefore, that mercury is going to show you 76 millimeter, right? So the question occurs, why we cannot use the water barometer? Why the mercury barometer, right? So we know that the height through which this mercury is rising is how much? 0.76 meter. So 1 meter instrument is okay, right? Here this much is, no, 1 meter is very big, right? So 1 meter, but we can take that 1 meter distance. It's not that bigger. We can carry that instrument anywhere. If you consider for this 1 atmospheric pressure, 1 atmospheric pressure means this 1.013 into 10 raised to 5. If I want to measure, consider this pressure is rho gh, right? How much it was? 10130. If I wanted to use the water, I know the density of water is how much? 1000 into G is how much? 10 NEH, right? If I do this calculation, what will happen? You can see this is 10130 divided by 1000 into it's another 0, I guess, right? Yeah, there is another 0. But it's going. Okay, let me write it again. 10130 1 into, and another 0 is there, 1000 into 10 into h. So if you do this calculation, your answer will be something like that, very bigger. H will become very 10 meter. You'll get the 10 meter answer. 10 meter means it's very high instrument. We cannot find a tube of 10 meter. You can actually, but it is not practical to take the 10 meter height instrument everywhere. Therefore, we do not use the water. Instead of that, we can use the mercury barometer here. Okay. Sure. So this is how we can measure the liquid, and so yeah. So this is the simple things we can say. Now let's. So this is the theory part of the whole chapter. We have seen the forces on the solids in previous two chapters, and here we have studied little bit about the pressure on the solids as well as pressure in the liquids, and we also know what is the atmospheric pressure, right? And we have also studied which instrument we can use, right? Which instrument? Mercury barometer. We cannot use water barometer, right? Why we cannot use the water barometer? Because that height becomes 10 meter. 10 meter is very high. We cannot take that 10 meter tube at everywhere, right? That's why we use the mercury barometer instead of water barometer. Now, let's see this question. Two identical blocks of wood are placed side by side on the table. So there are two blocks. One lies on the larger side and the other stands on the very smaller end. Right. So consider this. These are the two blocks, right, of the wood. This is one block, and the second block is also identical. They are saying on the same table. Consider we keep one block as it is, and the other block on the larger side, horizontal, right? So first will be vertical, and second will be horizontal. Which will exert the more pressure? At the start, we have seen this case, right? In terms of knife, pressure is directly proportional, or pressure is equal to what? F upon A. So if area is less, pressure will be more. So area in contact with this table, like this is our table, right? This is table, we can say. For this table, yes. Area in contact is less for which one? First or second block? First block, right? So what we can say, pressure in first block will be greater than pressure in the second block. Simple. Okay, so very easy question. Let's see the next one. A person whose mass is 50 kg and weight is 500 newton. We know, right? Mass is given. How to calculate weight, right? Weight is equal to mg. We can easily calculate it. That's not difficult one. So person whose mass is 50, mg is our formula for weight. G is approximately 10, so it will become 500 Newton, right? Okay. So has a surface area of on 1 feet is 0.01 square meter. So what pressure does the person exert on the ground if he's standing on the both legs? So now consider this is the person like this. He's standing on the ground. Right? Okay. We also have the hands, right? So what they are saying, question is weight is 50 kg. So how much force is he is applying on the ground? 500. So can I say force is 500 Newton? That's right. What is the area? Area of the 1 feet is how much? 0.01. So he has 2 feet. So what will be the total area? What we have to do? We have to add these two areas because there are 2 feet. So total area I can say will be how much? 0.01 plus 0.01. How much it will be? 0.02 meter square. I can say that, right? So now let's talk about the pressure. So if I know the formula, that is force upon area, can I say it is 500 upon 0.02? Right? If you do this calculation, you will get the answer almost equal to 2500 Pascal, right? Pascal is our unit. Atmospheric is also unit, but standard unit is Pascal. So whenever we do the calculations, remember we should write the unit in the Pascal. This is actually 25,000 Pascal. We will get the answer, right? Okay, how we do this calculation? Just move the decimal points. If you want to move the 2 decimal points, substitute the 2 zeros upward, right? So just dividing 50,000, I will get the 25,000 Pascal as our answer, right? Simple. Now, let's move to the next question. A thumbtack has a large flat surface and pointed end. What is thumbtack? You do remember it is a pin, right? Something like something which looks like nail, and we actually put this in the board actually, right? To stick any flyer or anything on this board, we apply this thumbtack, right? This is called as thumbtack. This thumbtack has a large flat surface area. This is the large surface area, and this is the pointed end. With the same applied pressure, which part will have the greater pressure? Now we have already seen at the start of the lecture, right? In case of nail and hammer, right? We should apply the hammer's force on this side. Similarly, this is the thumbtack. We don't need the hammer for this. Just put the pressure of your thumb on this flat surface. Then obviously that point will have the greater pressure. So which part will have the greater pressure? That point, we can say sharp point, right? This sharp point will have the greater pressure. Right? Obviously, you cannot reverse this and tie to. You cannot apply the force on that pointy thing, right? It will hurt your thumb, obviously. So sharp point will have the greater pressure. Why? Because area is less. The same concept, same principle. We already know that if the area is less, pressure will be more. Okay. Let's move to the next question then. What is the density of water, mercury, and ice? Right. So we have written this one. For water, the density is how much? 1000 kg per meter cube. We know for the mercury's density is very, very high than water. It is 13600 kg per meter cube. And what about ice? Now there is one concept. Remember that whichever material has the less density will float. Right? Simple. And I will repeat again. The material who have the less density will float. So tell me, if you put the ice in the water, ice floats or sinks, right? Ice floats obviously. So can I say ice density is less than that of water? That's right. Okay. So how much will be the density? Let's say it is 916 kg per meter cube. So remember this density of the ice, it is equal to 916 kg per meter cube. Okay. So we can use this density to find the pressure of the pressure which it acts on any object. We can say if the swimmer is in water, how much pressure it will act. Obviously we cannot swim in the mercury, right? Mercury's pressure will be very, very high, so we cannot swim in the mercury, right? But oil's pressure is very less, we know that part. So we can swim in the oil, but there is no ocean of the oil, right? Ice, we cannot swim in the ice, the solid part, right? So simple. So this is the whole chapter, we can say, right? So we completed the chapter of the forces, which we have seen the different forces also, and different types of the forces acting on the solids. What happens if you consider the forces on the liquid? For liquid, we have to consider the different concept which is called as pressure. What is the relation between pressure and force? That is, pressure is equal to force upon area. Pressure could be on solids also, or in liquids also. We can find out the pressure. For solids, we say that formula is force upon area. We derived another formula for the pressure in liquid, that is called as rho GH, where rho is the density. We also seen the atmospheric pressure. At the sea level, pressure will be very low. At the top level, mountain, on the top of the mountain, we can say pressure is very low actually compared to sea level. At the sea level, it will be higher. That is 1 atmosphere, right? So cooking will be easier at the sea level. as it is easier in our pressure cooker. We know that all, right? We have seen most of the concept of the pressures here, right? Okay, so this is the whole chapter. Now we are going to stop here. Obviously, if you do have any queries or questions, you can put those in the forum so I can answer those. Okay, so thank you very much. Have a nice day.